Hello students, in this video we're going to see how to find the local maximum and minimum values of the given functions using the second derivative test. Now in an earlier video we have seen how to find it using a first derivative test. I hope you recall that. We'll draw a number line and then we'll observe the how f dash of x behaves, like what is the sign of f dash of x before and after these stationary points, and based on that we'll find out whether it is a particular stationary point gives us a local maxima or minima, isn't it? Now in this video we are going to see how to use the second derivative test. Okay, now look at this diagram, students. Here you see a parabola y equal to f of x, and it has a local maximum at the point 4, 7, isn't it? So the 4 is a stationary point here. The 4 that you see here is a stationary point, and of course you are aware why it is a stationary point, because f dash of 4 equal to 0, isn't it? F dash of 4 equal to 0. Okay, here f of 4 is 7. F of 4 is actually 7. So 7 is this is the local maximum value. This is the local maximum value. Okay, now if I draw a number line here, let's say if I draw a number line, now from the graph it is very obvious that before 4 the function is increasing, isn't it? Here before 4 the function is increasing, and after 4 the function is decreasing. F of x is decreasing. So it is quite obvious that at 4 you get a local maximum. Now when we use the first derivative test, I hope you recall that we'll write 4 here, then we'll take a value greater than 4 and then you substitute in the first derivative and try to find the sign. In this case it will be negative. F dash of x will be less than 0, isn't it? Because f of x is decreasing. And if you take a value before 4, less than 4, and substitute in the first derivative, you will find that f dash of x will always be positive. Now from this also it is very clear that, okay, in fact without drawing the curve, using this number line alone, we will deduce whether the function is decreasing or increasing before and after 4. Yeah, that is how we determine whether 4 gives us the local maximum and minimum values. Okay, what if I want to find the sign of f double dash of 4? Okay, what if I want to know whether f double dash of 4 is equal to 0 or positive or negative? How can I find that? Can I actually find it? Yeah, definitely. Now let us understand something. We know that if f of x is increasing, means f dash of x is positive. If f of x is decreasing, implies f dash of x is negative, isn't it, students? Yeah, same way, if f dash of x is increasing, it means f double dash of x will be positive. If f dash of x is decreasing, then f double dash of x will be negative. Yeah, so I'm going to use this concept to find out whether f double dash of 4 is positive or negative or 0. Okay, now you please observe this given graph. Before 4 f dash of x is positive, and after 4 f dash of x is negative. Now this is, I told you, a parabola. Yeah, so this is the graph of the original function. Now when I find the derivative of this function, when I find differentiated, parabola is it will give me a quadratic function. So when I differentiate it, I will get a linear function, isn't it? So the graph of f dash of x will look like this. Okay, let me erase this part. So okay, now this is how I'll draw y-axis here, and let me draw x-axis. So this is x, this is y. So now since f dash of 4 is 0, okay, so I'm sorry, this is not yeah, this is in fact dy by dx. In fact, this is not y, this is because I'm going to draw the graph of f dash of x. So this is going to be f dash of x. Okay. Now, since f dash of 4 is 0, the curve, this is 4, right? The graph of the derivative will intersect x-axis at 4. Okay. Now you can see f dash of x is before 4, f dash of x is positive, and after 4, f dash of x is negative. So this is the positive side, right? And this is the negative side. This is the positive side and this is the negative side, isn't it, students, for f dash of x? Okay. As I told you, the derivative will be a linear function because the original function was a parabola, so a quadratic function. So derivative will be a linear function. So linear function is nothing but when you represent it in the graph, you'll get a straight line, and you'll get a straight line like this. Yeah. So this is the graph of f dash of x. Now, as you can see, this graph, this f dash of x is a decreasing function, isn't it, students? Yeah, you can see it very clearly. It is a decreasing function. So hence, just we saw if f dash of x is decreasing, then f double dash of x is negative. So since this f dash of x is a decreasing function, f double dash of 4 will be negative, will always be negative, right? So f double dash of 4 is negative when 4 gives us a local maximum value. I hope you've understood what I'm trying to say. So whenever a particular value of x gives us a local maximum value, in fact you can check with more examples, but I'm not going to do that. Okay. So in fact, whenever you take any stationary point which gives us a local maximum value, when you substitute that value in the second derivative, you'll always get a negative answer whenever f double dash of x exists. Okay. So okay, let me take another example. Okay, now let us see another diagram now. So in this particular scenario, in this particular diagram, you can see that at 3 we get a local minimum value which is 1. So we know that f of 3 is 1, which is the local minimum value, and f dash of 3 is 0 because 3 is a stationary point. Okay, now again, what if we want to find the behavior, or what if we want to find the sign of f double dash of 3? I want to know whether f double dash of 3 is positive or negative or 0. Okay, so for that I need to draw the graph of the derivative function. This is the original function and it is a quadratic function. Now since this is a quadratic function, the derivative will be a linear function. Okay, but let us observe something here. When you draw a number line and mark 3 here, after 3 f dash of x is positive, isn't it, students? Because the function is increasing. The function is increasing here, so f dash of x is positive. Now before 3, since here the function is decreasing, f of x is decreasing, what I'll get is I'll get f dash of x less than 0. Yeah. So before 3 f dash of x is negative, and after 3 f dash of x is positive for all values of x. Okay. So let me draw the graph of the derivative function. From that I can find out whether f double dash of 3 is, whether this f double dash of 3 is positive or negative or 0. Okay, so let me draw it now. Okay, now f dash of x, so this is x and this is f dash of x, so it will be a linear function f dash of x. It will intersect the x-axis at 3, isn't it? Because f dash of 3 is 0, so 3 is here, let's say 3 is here. Now before 3 f dash of x is negative. So as I told you earlier, this is the negative side of f dash of x, and this is positive side of f dash of x. Okay, so before 3 it will be negative, so that means the curve will look like this, and after 3 f dash of x is positive. So here, so this is the graph of f dash of x, the function f dash of x. Okay, now from this, can you find out, tell me whether f double dash of 3 is positive or negative, students? Very clearly, it is very obvious, because f of x, f dash of x is increasing, isn't it? Here f dash of x is increasing, so f double dash of 3 will be positive, definitely positive. Yeah, so whenever f of x is increasing, f dash of x is positive. Same way, whenever f dash of x is, wherever f dash of x is increasing, for those points f double dash of x will be positive. So here we saw that 3 is a stationary point which gives us a local minimum value. So, but when we substitute the 3 in the second derivative, we get a positive answer. Yeah. So let us summarize what we have learned in this video till now. Okay, so this is what we learned. If x is equal to a is a stationary point, and if it gives us a local maximum value, then f double dash of a will always be negative, provided if the second derivative exists. Now if x equal to b, the second line, if x equal to b gives us a local minimum value, then again f double dash of b will be positive, provided the second derivative exists. So you can say local maximum means second derivative is negative, local minimum means second derivative is positive. Okay, so let me solve some problems to make it clearer. Okay, now let us look at this problem. I would like to find out whether this particular function has any local maximum or minimum values, and if they do, if this function does have it, then what are they? Yeah, so I'm going to use the second derivative test. So first you need to find the stationary point. For that you need to find the first derivative. So f dash of x equals derivative of x cube is 3x squared minus derivative of 27x is 27 plus 0. So 3x squared minus 27. Now to find the stationary points, you need to equate the first derivative to 0. So 3x squared minus 27 equal to 0. So it will give me x equal to plus or minus 3, right? X squared will be equal to 9, so x will be plus or minus 3. Now earlier you used to draw a number line, and then we found the sign of the first derivative, but let us use the second derivative test now. So I'll find f double dash of x, which is nothing but, I have to differentiate this, so 6x. So f double dash of x is 6x. Okay, now I will substitute these stationary points in the second derivative. So first I'll substitute 3. So f double dash of 3 equal to 6 into 3, 18 positive. So I hope you recall, if the second derivative is positive, then we'll get local minimum value, isn't it? So this implies x equal to 3 gives local minima. Okay, now how do I find that local minimum value? Very simple. You substitute this 3 in the original function. Okay, so if I want to find the local minimum value, so local minimum value is nothing but f of 3, which is nothing but 3 cube minus 27 into 3 plus 9. So it will give me 27 minus 81 plus 9, so minus 45. So minus 45 is the local minimum value, right? Very simple. Okay, now we still have one more stationary point, minus 3. So let me substitute in the second derivative again. So f double dash of minus 3 equals 6 times minus 3, which is minus 18 negative. Now again, we know that if the second derivative is negative, then we will get a local maximum value. So x equal to minus 3 gives us local maxima.
Okay, now how do we find the local maxima? Again, very simple. Substitute this minus 3 in the original function. So what I'll do is I will do it here. Local maxima equal to f of minus 3, which is minus 3 the whole cube minus 27 into minus 3 plus 9. So it will give me minus 27 plus 81 plus 9, which is nothing but 63. So this minus 45 is the local minimum value, and this plus 63 is the local maximum value. So problem is over. So very simple. Okay. So let us solve another problem now. Now if f of x is equal to x cubed minus 6x squared plus 8. Now I want to find the local maximum or minimum values if they exist using the second derivative test. So first let me find the first derivative. F dash of x equals 3x squared minus 12x plus 0. Right? This is the derivative, first derivative. Now I need to find the stationary points. For that I need to equate it to 0, the first derivative. So 3x squared minus 12x equals to 0. This implies 3x into x minus 4, I'll factorize it, equal to 0. This gives me two stationary points, x equal to 0 or 4. Right? So let me find the second derivative now. F double dash of x equal to 6x minus 12. Okay. Now I would like to know whether these two stationary, whether 0 will give me a local maxima or minima, same way whether 4 will give me a local maxima or minima. So how do we find out? Very simple. You substitute these values, these stationary points, in the second derivative. So first let me substitute 0. So f double dash of 0 equal to 6 into 0 minus 12, which is minus 12 negative. So which means second derivative is negative, means x equal to 0 gives me local maxima. Right? Now, can I find the local maximum value? Definitely I can. So I have to substitute the 0 in the original function. So f of 0 equals 0 minus 0 plus 8. So this 8 is the local maximum value. Now let me substitute the second stationary point in the second derivative, f double dash of 4, which is, so I have substituted here, so 6 into 4 minus 12, which is 12, so positive, which means x equal to 4 gives me local minima, right? So to find the local minimum value, I'll substitute the 4 in the original function. So f of 4 equal to 4 cube minus 6 into 4 square plus 8. So this will give me 64 minus 96 plus 8. So the answer is minus 24. So this is the local maximum value and this is the local minimum value, right? Very simple. So let us see one more problem now. So let us look at this quadratic function now. F of x equal to x squared minus 6x plus 2. So let me find the first derivative first. F dash of x equal to 2x minus 6. So I need to find the stationary point. For that I will equate the first derivative to 0. So 2x minus 6 equal to 0 implies x equal to 3. Okay. Now I'll find the second derivative. F double dash of x equal to, I'll differentiate 2x minus 6, which is 2. Okay. Now normally we will substitute the stationary point in the second derivative, but in the second derivative there is no x to substitute. But straight away we know that f double dash of x is 2 always. Whatever you replace it, whatever you substitute for x, f double dash of x will always be 2, so it will always be positive. So if f double dash of x is positive, it means that x equal to 3 gives us local minima. First, second derivative is positive, means local minima. So to find the local minimum value, to find that local minimum value, I'll have f of 3, which is 3 square minus 6 into 3 plus 2. So I'll get minus 7 as the answer. So minus 7 is the local minimum value. Okay, let us see one more problem. Let me take this one. F of x equal to x minus 1 into x squared minus 4. Okay, now I can either find the first derivative using the product rule, or I can simplify this function and then find the first derivative. So let me simplify this function. So I'll get x cubed minus x squared minus 4x plus 4. Okay, so let me find f dash of x. So f dash of x equals 3x squared minus 2x minus 4. Okay, so I need to find the stationary points here. So I need to equate to 0. So 3x squared minus 2x minus 4 equal to 0. Okay, now this quadratic function, a quadratic equation will give me irrational roots. You can see that it's very simple. You can't factorize it. So let me use the GDC. So using GDC, the solutions of this quadratic equation are 1.54 and minus 0.868. So these are the two solutions. So let me find the second derivative. F double dash of x equals 6x minus 2. So I have to substitute each one of the stationary point in the second derivative. So f double dash of 1.54 is 6 into 1.54 minus 2, and you can easily see that this will be a positive value. So this means x equal to 1.54 gives us local minimum. Okay, and that local minimum value is f of 1.54, which is 1.54 minus 1 into 1.54 squared minus 4. So let me use the calculator for this. So I'll get minus 0.879. So this is the local minimum value. So let me find the second. Let me substitute the second stationary point now. F double dash of minus 0.868 in the second derivative. So 6 into minus 0.868 minus 2, and you can see it very clearly that this will be negative, which means this x equal to minus 0.868 will give me local maxima. Okay, how do you find that local maxima? Very simple. Let me find it here. So local maximum value is f of minus 0.868. So I can substitute it either here or here, then I will get this answer. Okay, so I'll get 6.06. Okay, so this is the local maximum value. Very simple. Okay, now last problem for this video. Okay, let us consider this problem, students. F of x equal to 4x cubed minus x power 4. So let me find the first derivative. F dash of x equals 12x squared minus 4x cubed. Okay, I have to find the stationary points. Let me equate the first derivative to 0. So 12x squared minus 4x cubed equal to 0. So let me factorize it. I can take 4x squared common, which will give me 3x minus, It'll give me 3. I'll get 4x squared common. I'll get 3 minus x equal to 0, which means either x equal to 0 or x equal to 3. Okay, let me find the second derivative now. F double dash of x is 24x. So I have to do, I'm differentiating this, minus 12x squared. Okay, so let me first substitute 3. So f double dash of 3 equals 24 times 3 minus 12 times 3 squared, which is nothing but 72 minus 108, so negative, which means x equal to 3 gives local maxima, right? And that local maximum value is f of 3, so which is nothing but 4 into 3 cubed minus 3 power 4. So again I'll get 108 minus 81, which is nothing but 27. So 27 is the local maximum value. Okay, we still have one more stationary point, which is 0. Let me substitute in the second derivative. So f double dash of 0 is nothing but 24 into 0 minus 12 into 0 squared, which is nothing but 0. Okay, now we know that if the second derivative is positive, we get a local minima. If the second derivative is negative, then we'll get a local maxima, right? But what if the second derivative is equal to 0 then? What will we get? Okay, we all know that it may be a point of inflection, not will be, it may be a point of inflection, or it may be a point of maxima or minima. Okay, then how do we find out whether the stationary point 0 will give me local maxima or minima, or whether it will give me a point of inflection? Now in this case, we say that the second derivative test fails. Okay, we can actually use the first derivative. So what I do is I take I draw a number line, and I write 0 here, the stationary point. I'll take a value more than 0. Let me take 0.1 and substitute in the first derivative here in this one. So let me check it. So I'll find okay, for convenience sake, let me take a better value instead of 0.1. Let me take 1. So f dash of 1 will be 12 minus 4, which is 8, so positive. So here f dash of x will be positive. So let me take a value now here. And let's say, let me take minus 1. So f dash of minus 1 is 12 into minus 1 the whole squared minus 4 into minus 1 the whole cube. So it will give me 12 plus 4, again positive. So f dash of x is positive. So you can see that the first derivative does not change its signs before and after 0. So and also we know that f double dash of 0 is 0. So it very clearly states that the 0 is a point of inflection. So x equal to 0 gives us a point of inflection. In fact, it is a stationary point of inflection because 0 is a stationary point, right? So whenever you get, whenever the second derivative becomes 0, you need to use the first derivative test because it may be a point of inflection or it may be a point of maxima or minima. Okay, I'm going to show you, explain this with the last problem for this video. Let me take f of x equal to x bar 4. Okay, now f dash of x equal to 4x cube. So let me equate that to 0 to find the stationary point. 4x cube equal to 0 implies x equal to 0. Now let me find the second derivative, f double dash of x, which is nothing but 12x squared. Now let me substitute the stationary point in the second derivative. So f double dash of 0 equal to 12 into 0 squared equal to 0. Okay, as you can see, the second derivative is 0. So does that mean we'll get a point of inflection? Need not be. So what you need to do is, in that case scenario, we need to draw the number line, and you put the stationary point, which is 0 here, and take a value more than 0. Let me take, let's say, 1. So, and substitute in the first derivative, not second derivative. So f dash of 1 is 4 into 1 cube, which is 4, which is positive. So f dash of x is positive whenever x is more than 0. Now let me take a value less than 0. Let me take, let's say, minus 1 and substitute in the first derivative. So f dash of minus 1 is 4 into minus 1 the whole cube, which is minus 4, which is negative. So f dash of x is negative. Now as you can see, before 0 f dash of x is negative, which means f of x is decreasing, and after 0 f dash of x is positive, means f of x is increasing. So the curve looks like this. F of x is decreasing, so it comes down, and then after 0 it increases, so like this. So as you can see, you won't get a point of inflection. In fact, you will get a point of minima, isn't it? So x equal to 0 gives us a point of minima. To verify this, let me actually draw the graph of x power 4. Okay, let's say this is y-axis, this is x-axis. I'm sorry, let me draw it properly. Okay, now this is how x power 4, y equal to x power 4 look like. As you can see, at 0 you are getting a local minima. So from this it is very clear that if the second derivative is 0, it may give us a point of inflection like in the previous problem, or it may give us a local minima like we have in this problem. Similarly, it may also give us a local maximum. So the only way to find out is to draw the number line and then observe the behavior of the first derivative before and after the stationary point, right? So I hope you are very clear with how to find the local maximum or minimum values using the second derivative function. Yeah, thanks for watching this video.